So let's take a look now at example 8, and we're going to try to put all of this information together at once to try to, without the use of any technology whatsoever, figure out a good sketch of the following function. So as you see here, I'm going to ask that we find where does this function increase, where is it decreasing, where is it concave up, where is it concave down, where are the local extrema, where are all the inflection points. Let's find all of it. And then can I piece that together to figure out what this graph looks like? So what I'm going to do here to help try to organize my work is to kind of think about what my first derivative here, again, is useful for helping me find. So I'll start here with my first derivative of my function. Now, I can calculate that derivative out, and I get 3x squared minus 3. There's not much to it here. Now, of course, I recognize I could rewrite that as maybe 3 times x squared minus 1, or I could write that as 3 times x minus 1, x plus 1. So there's my first derivative. Now, if I want to go ahead and find critical points for this, remember, I can find things like where's the graph increasing and where's it decreasing, and I can also use first derivative test to find where it has local mins and maxes. So let's go ahead and do that. I'm going to see that f prime of x is equal to 0 when, well, this is easy, when x is equal to plus or minus 1. And I can also see here that f prime of x is never undefined. Right? It's never undefined at all. So I'm going to go ahead here and I'm going to take all this information, put it on a number line, x, and my first derivative. Okay, so I have negative 1, positive 1. I know this makes the first derivative spit out zeros. Now I can test some other values on either side. Let's start with maybe something like negative 2. Notice if I start with negative 2, this piece would be negative, and this piece would be negative. So I'm going to have negative times a positive 3. That's ultimately going to result in something positive. I can then also plug in something like 0. That's going to get me a value back that is negative. I can plug in a value then of, say, 2, and I can see that that's going to get me back to positive. So I can think then about what the graph is going to look like. The graph I know is going to go up and then down, and then it should go down and then up. So I'm going to have a minimum value at 1 and a maximum value at negative 1. So let's summarize all of this here over on the side. I can say that f of x is increasing on the intervals from negative infinity to negative 1, and also from 1 to infinity. It is decreasing on the interval from negative 1 to positive 1. Great. I can also then see that I'm going to have a local minimum of, let's see, this would be f of 1. If I go to my function and I plug in the value of 1, I'm going to get 1 minus 3 plus 2. That's just going to be 0. I can also then see that I get a local max of f of negative 1. So that's going to get me negative 1 plus 3. Negative 1 plus 3 is 2. 2 plus 2 makes a total of 4. Wow, so I found a ton of information out about my function very quickly, all from my first derivative. And now let's try to go ahead and take a look here at our second derivative. My second derivative is obviously going to require that, well, I calculate the second derivative, and I'm going to use this simplest form over here of f prime. Notice that's just going to get me 6x. This is a really, really easy second derivative. I can see that f double prime of x is equal to 0 when x is equal to 0. And I can also see that f double prime of x is never undefined. So if I put this information on a number line, oops, I would have my values of x and my f double prime of x. I can see that at 0, I know my second derivative spits out 0. Clearly, if I plug in a negative number, I'm going to get a negative. And if I plug in a positive number, I'm going to get a positive back. And so I can see here on this interval, my graph is concave up, and on this interval, my graph is concave down. Notice again, there should be a maximum somewhere below 0 and a minimum somewhere above 0, which is exactly what we found up here. Everything's consistent right now. So I'll go ahead and summarize this over here as well. I'll state that f of x is concave up on the interval from 0 to infinity. It is concave down on the interval from negative infinity to 0. And we have an inflection point of 0, comma, and I'd have to go all the way back to my original function to find the point on the graph. Notice if I plug in 0, I would get 2 back. So 0, comma, 2. So now that I have all of this information, I can start to go ahead and see a couple things. First, I can see what each derivative again is good for. First derivative can tell me increasing, decreasing, local mins and maxes. Second derivative is good for concavity and inflection points. But now that I have this, I can take all of this and kind of put all of this together to try to create the picture of this function. So let me go ahead and see if I can try to sketch this out here on the graph of this, or on the set of axes that I've sketched out here. All right, so let's see what we're going to have. So first off, I can start by maybe plotting a couple of the points that I actually know for sure are going to be here on the picture. I know, for instance, 0, 2 is going to be on the picture. I also know that something like -1, 4 is going to be up here on the picture. So -1, let's say this is at 4 and this is here at 2. I also know that 1, 0 is on the picture. And I know that this point up here is my max. I'll label it. This is a max. This point down here is a min. And this point right here is an inflection point. Okay, so how do I start to put the rest of this information together in order to sketch the picture? Well, I'm going to show you at least the way that I believe to be the easiest. Now, you might disagree with this approach, but I think it's the best and the easiest way. So I'm going to recommend that you at least give it a chance. Here's what I like to do. I like to start by just producing a rough picture of the graph. So I'm going to start by focusing on where my graph is increasing and decreasing, and I'm going to draw it in a very kind of rigid shape. I know that my graph is increasing from negative infinity to -1. So watch how I'm going to draw this. I'm just going to draw a straight line from negative infinity off to -1, just like this. I then know that my graph is decreasing from -1 to 1. I might be able to more easily follow that by looking at this number line. From -1 to 1, my graph is decreasing. So I'm just going to draw kind of like a straight line that connects the dots. Okay, there we go. And now I know that after 1, my graph goes back up. So here's a rough picture of the graph. But what I haven't accounted for yet is the second derivative. It's the bendiness of the curve, the concavity. But now what I can do is I can try to go ahead and reshape or remold the curve so that way it actually fits with these appropriate sorts of bends. So notice here on my number line, in the second derivative, I can see that from negative infinity to 0, the graph should be concave down. It should be bending in this downward direction. So what I'm going to do is I'm going to go back here and I'm going to erase these two portions of the graph. I'll leave this portion in, but I'm going to erase those two portions and I'm going to kind of reshape them. They're supposed to be kind of bending downward, kind of like this picture looks over here. So I'm going to imagine that I'm going to go all the way up to the top here and then bending downward, something like this. Okay, so that's concave down. Now I realize that from 0 onward, I should be bending in an upward fashion. So I'm going to erase these two kind of really rigidly straight portions, and I'm going to reshape them. So they kind of bend in a more upwards direction, kind of like this. And now I have a picture of the graph. Now the cool part is that if I was to go to some technology and actually take a look as, is this actually what the graph looks like? Well, I can actually see that, yeah, it is. Take a look. If I pull up a calculator here and I have my function typed in, is my x to the third power minus 3x plus 2. If I hit the graph button, notice it looks exactly like the picture that we just constructed. Moving down, concave down here, at this inflection point, the concavity switches, and I go back to concave up. very similar to the picture that we have. Maybe ours is just a little more spread out, whereas this picture is a little more squished. But if I was to maybe even just change the window a little bit, maybe I go from like, say, -3 to 2. If I was to do that, yeah, this is starting to look a little bit more like the picture that we had, right? Little bit closer. Not exact, but a little bit closer. So we have a really good sense of what this graph looks like just by combining all of this information that we have here.